Alexander Galybin from Schmidt Institute of Physics of the Earth, Russian Academy of Science, and the title is very, very related to the topics of the workshop, so not afraid.
Yeah, thank you very much, Mr. Chairman. First of all, I would like to thank the organizer for inviting me here and giving possibility to deliver this talk. Well, it will be on application of the Wiener-Hopf technique to a special type of incorrectly posed problem of plane elasticity. Well, that is brief outline of my talk. I mean, I will spend few slides to introduce motivation and background, and then we discuss three possible boundary value problems where I would like to show a relationship between singular integral equations, their solvability, and also the Riemann boundary value problem, and we will try to get analytical solution here. So that slide I just put it to show which way I go to in order to get the Riemann problem or Wiener-Hopf problem. I mean, normally people just start from a system of partial differential equations, and then for simple contours you can apply integral transforms and immediately get the system of Wiener-Hopf equations in the domain of, I mean, for images, not in the physical domain, but in the domain of the parameter of integral transform. Right, and then after that, in general, you should invert this, the solution, right? So second idea is go to the system of singular integral equations from here, which can be easily done, especially for classical formulations, because we already have Kolosov and Muskilishvili formulas, and then in terms of complex potentials, it's quite that it's not expensive. I mean, step, right? So you can derive this system quickly, and then again apply integral transform, get exactly the same system of Wiener-Hopf equations, and again you will need to inverse it, right? So you need to apply the inverse integral transform in order to analyze, for instance, stress field in particular problem. So I'm using a more classical way, as in books by Muskilishvili or Gahov, right? So from this system of equations, what I'm doing, I mean, I just separate the dominant part of the integral equation, and then use the properties of Cauchy integrals in order to get Riemann boundary value problem, which is in this case would be on, it's again, I mean, it's restricted to simple contours, but in this case I don't need to perform integral transformation of the solution. I would like to say that in all cases we still need factorization, of course. So, we cannot come up, we cannot get rid of it, but perhaps if we use this way and try from this system of Wiener-Hopf equation, if we try to obtain the equivalent system of singular integral equations for images, maybe in this, if we do like that, perhaps we can skip factorization, but I'm not quite sure. I mean,
I think this is what people
on
this workshop.
A couple of people. Yeah, that's right. I mean, but what I heard, it was a kind of Fregon regularization. But what I'm saying, I mean, that singular integral equations can also work for this case, right? Well, so just a little bit different stuff. I mean, why we need to consider special type of boundary value problems? Say they originate from the idea of how can we study the stresses in the Earth's crust, for instance, right? Because unfortunately, we don't have reliable information on displacements and tractions on the margins of tectonic plates, and therefore we are not able to formulate standard boundary value problems, say in terms of tractions or displacements or mixed boundary value problems. But instead we know, well, we know the directions of the movement, right? For instance, these red arrows, they show how in the Australian plate, so this part of the picture, this is in the Australian plate, and yeah, nowadays they consider two plates, Indian and Australian, but I mean in the past it was just in the Australian plate, and that is a part of the big Euro-Asian plate. It's presented here by Burma microplate and Sunda plate, right? So that region is very well known, I mean, because of very high seismicity there. If you remember, in 2004, it was great earthquake that generated tsunami, and as a result, I mean, many people were killed. So, of course, understanding what kind of stress field in this region could be beneficial maybe for understanding of geodynamics of this particular region. Well, so we know the directions, but as I said, we don't know actually the magnitudes of these displacements, and we also know orientation of the principal stresses. They are shown here by these segments, green color and blue color. I don't want to go into detail why they are different color, but I mean it makes sense for geophysicists, right? Well, for geomechanics, it's important that these segments, they present direction of the principal stress, which is maximum compression, right? Well, so you can see, for instance, that I mean from this side you have a lot of blue directions shown here. They're almost perpendicular to the boundary, and from other side they tend to be parallel to the boundary. Well, I will show you later that this case. Well, I think we discuss it maybe a little bit later, but what I'm trying to say, a lot of data are available now. It's about 40,000 data, and there is special geophysical project called World Stress Map Database. So you can get all the data and work with it. They're free to use, right? So the idea of this research is to use this data to this specific information in order to provide stress analysis in tectonic plates. Well, it's not the first publication. The first one was 20 years ago in the Journal of Mechanics of Physics of Solids, and we were very grateful to Professor John Willis, who was an editor at that time of this journal and who accepted our paper for publication. Then with different intensity, I was doing sometimes different modifications, so consider different problems. But I mean that one was really the first one. And what we managed to show there, that if you consider boundary value problem in terms of orientation of principal stresses and displacements, then this problem can be solvable, but it may have several so it loses non-uniqueness, right? There could be several solutions, independent solutions. The number of this solution is finite, and therefore you can construct the whole solution as a linear combination of these particular solutions. Therefore, if we are able to solve this problem, we would still have several constants which we cannot determine from the problem. But if we, for instance, make some experiments or whatever, where we can get information regarding the magnitudes of stresses, then we can recover those constants, right? So that I am not going to talk about the second part. I just want to present the first part, right? Now that is a background. Fortunately, Gachov, in his famous book, presented a good way how to work with the equation of such type. Here we have G is unknown function, its conjugate, as G is the Cauchy type integral, its conjugate and couple of regular operators. So in the right hand side, in general, we can have non-zero, right? But I mean, in this particular case, it would be homogeneous problem, right? Well, so the idea is provided by Gachov. He showed how to reduce this problem to a standard integral equation that does not have conjugation terms. I mean, this term and that term disappears, but of course it would have different coefficients, not A and C now, but it's missing somewhere here, but it would be coefficients A and B, right? And therefore the solvability of such problem depends on the index, which index of the standard integral equation, or index of the boundary of the Riemann boundary value problem, which is presented here, and that is the connection of this A and B function with ABCD function, which is shown here. So what we have to say is that if index is positive, index 2k is positive, then the solution exists, and it depends on two kappa complex constants, or if I count them as two real, then it would be dependent on 4 kappa real constants. Otherwise, solution does not exist, but it does not exist if the right hand side is 0. If it's not 0, then we have a unique solution. And that unique solution, I mean, if I go from this equation, for standard problems A and B are 0, and therefore you can check by inspection that then in this case the index of the problem is equal to 0, and therefore all of them have unique solutions. So that type of equations covers as traditional formulations as incorrectly posed. Now, what I have to say that first of all, solvability of that equation depends only on the dominant part, and therefore I can remove regular operators. So mechanically it means that we will consider the case of elastic half plane. Also, almost similarly, you can consider the case of unit circle, for instance. Just a couple of constants should be added to the solution, right? Well, but for our case, which I formulate, I mean, just on the next slide. The right-hand side is 0, and therefore we have to consider such equation, from which it's quite obvious that you cannot apply any numerical methods directly, right? Because the right-hand side is 0, so we'll get trivial solution. But unfortunately, there are more complications also. For some combination of boundary conditions, you are not able to get this equation, and I will show you what kind of equation we can a little bit expand the Gacha's result. Right. So let me quickly present, formulation of the problem. So if I introduce the complex stress deviator like this one, the function d, then its modulus is the maximum shear stress, and its argument is connected to the principal direction of the stress tensor, right? So this function is biholomorphic. It means that its second derivative with respect to conjugated variable vanishes. And that is the complex displacement vector. It could be, again, it's presented like this, where in this form where beta is the direction of the displacements, and it satisfied the Lamé equations. It's not like the function d, actually. Well, what we do next? We're using covers of potentials. We present them as the Cauchy integrals with unknown densities g or g prime, right? And substitute into the previous formulas in order to, and then we can get the boundary values. They denoted like d plus minus or w plus minus. Of course, but just simply by using the Sachotsky-Primé formulas, right? In this formulation, the condition of continuity of the stress vector across the boundary, across the interface is already preserved, so it's satisfied automatically. So that is the condition, boundary conditions I'm going to use. So we know the argument of the function d and argument of the function w, right? And as I said, nothing is known regarding the magnitudes. So 3 problems are shown here for connected half planes, right? The first problem is actually, I call it alpha p, but that is the underspecified problem. We use it as an auxiliary problem here, right? So it means that we know argument of the function d plus, or in other words, directions of the stresses, principal stresses, right? For the upper plane and lower plane. And continuity is also, as I said, continuity in all formulations of stresses, stress vectors or tractions, whatever, through the interface is preserved here, right? Second problem is we also know directions of the displacements, and the third problem we consider either upper. In this case, I consider upper half plate and specify the directions of stresses and displacements, and nothing is specified for the lower half plane. Now, how to derive the system of equations? So what we use here, we know the argument of function d. If I multiply this function by exponent to the power minus I alpha, I have real valued function, and therefore its imaginary part of it is equal to 0. That is the first equation, actually. When I replace this d plus and minus with the relationship that I showed on the previous slide, we will have such 2 equations. And similarly for this case, we also have 2 equations. So we at the moment we have four it's not even equations. These are equations. We have 4 equations, right? Now let's work out. I mean the first case, which is denoted by asterisk. So what we can see here, we have G prime plus G prime conjugate, so it's real part of G, and therefore I can introduce a new function which is mu, which is real valued, and then immediately these 2 equations becomes like this one, right? So then we can combine it, as these 2 scalar equations can be combined in one complex dominant equation of the Wiener-Hopf type, right? It has such form. Of course, I use the properties of the singular operator for the real axis, and that makes all these computations to be much more simple. From here, we immediately get the Riemann boundary value problem. That is the solution for the case of real axis, taken simply from the Wiener-Hopf's book. It takes into account one possible poles and whatever, and not poles, I mean zeros. And that is the index of the problem, which you can see that the index depends on the difference of the stress orientations on the upper boundary and lower boundary. So it can be it can be any number, positive or negative. If negative, then solution does not exist. I mean, it does not exist in the class of analytical functions. If I introduce poles, then it can exist, of course, right? Well, and that is solution for the function mu, which was a known function in the integral equation. Now, but that's, as I already mentioned, that solution is incomplete because the stress deviator can be presented as the sum of 2 terms, and we found solution based on this term, and second term it goes to 0 because we have here product z conjugate minus z, so that becomes undetermined. However, even this solution, which is not complete, fully not complete, right? It has some sense because it can be used to analyze how the stress trajectories behave near the interface. For instance, this stress trajectory that is a curve. If I draw tangent to any point, it shows me direction of the stresses, principal stresses, right? So, oops. Such behavior is not possible. It's very similar to the refraction law, right? It's not possible because in this case the condition that the maximum shear stress is positive is not satisfied. But these 2 cases are admissible, and one of them I already mentioned. I mean, this case, remember when I showed the diagram, right? So it was very similar to this one. Well, now the second problem, we will add information regarding the orientation of the displacements. So if we combine the other 2 scalar equation into one complex, we get this expression. So it looks we have these G conjugated terms, but we are lucky we can easily get rid of that because I can replace G conjugate as 2 mu minus G function, but we already found solution for the mu function. So that goes, I mean, these terms goes to the right hand side, and that is the left hand side, right, which is actually standard dominant singular integral equation, which can be easily solved or first of all reduced to the Riemann problem, and it can be shown that the index of this equation is 0. Therefore, the solution of this equation has kappa plus 1 independent solutions, right? Well, and the third problem is here. In this case, I can drop the indexes because I consider only the upper plane, so that would be the this would be the boundary conditions. That is what we have from the first boundary condition, so that is real. That is system with respect to real function, unknown function mu, and that the second one is the complex function g. But as I said already, we can replace it because we can solve this equation. We can solve it, we can substitute the solution into second one, and therefore that would be the system of equation what we are trying to solve. Look, in this case, I mean, I can consider the second equation, I can decompose it, and then it would be 2 by 2 matrix, right? If you do it in standard form, but and that is not the first one cannot be included into this one because we have the function mu, which is the derivative of the real part of the unknown function. So it's not like Gahov's case, and that is not like simply 2 by 2 matrix, right? In Wiener-Hopf factorization problem. But we are lucky here because we can after such substitution we can get diagonal matrix, right? Or in complex form we simply have such equation instead of second integral equation like here. Well, the first one is simple, we already solved it, and the second one is also simple, but it just non-homogeneous equation. So that is the solution of the first homogeneous equation. I have to, yeah, it's almost close. I have to say that the coefficients of these polynomials should be real in order to provide real valuedness of this function, and the coefficient of that polynomial should be also real to provide real valuedness of the function lambda. And here kappa and n are partial indexes of the problem, and therefore they are defined as follows, right? They show actually they're proportional to the number of rotation of the say displacement vector like here, or orientation of the principal axis of the principal stress, right? And therefore we can, I mean, if I want to know how many parameters will be included in my total solution, then it's simply the sum of these partial indexes plus 1. This one is just due to integration, just one extra constant. So, and the last point I want to make, I mean, the first problem, for instance, or the second problem, for instance, can be unsolvable. Well, however, both the total problem still has solution, provided that the index of the first problem is greater than the index of the second problem. Absolute value of the index of the second problem. So in summary, I just want to say that we investigated here couple of problems which are incorrectly posed, and also we managed to develop a little bit of Gahov's approach and extend it for the case when we have derivative as unknown functions. Thank you very much.
Very short remark. As we can see here, you show the two different cases of boundary value problem. One-sided problem, and second two-sided problem, and of course they are solved in a slightly different way. This is a
I
core.
would say they solve, I mean, iteratively, or I mean, one by one. So a kind of successive approach here.
Okay, thank you very much.
Thank you.